Alright, we're going to do Giancoli Chapter 4, number 47. We're taking a box and sliding it across the floor. The floor is frictiony, so before I even read the rest of the problem, I can tell you that it's going to look something like this. And that means I'm slowing down, right? And my force diagram for the box, I'm going to have the ground pushing up. I'm going to have the Earth pulling down. There's nothing pushing it to the right, but there is kinetic friction, which is mu sub k times the normal force, pulling it to the left. So my acceleration is to the left. I'm going to call right and up positive anyway. It's moving to the right, and you could do it either way. It's up to you. You're just going to have to be careful with your signs, either of the velocity or of the acceleration, depending on which way you do it. The F net in the y, n minus mg is 0, and in the x, the forces are not balanced, so I have negative mu sub k times the normal force equal to ma, because those are the forces on my box of mass m. Alright, now I'm going to read the rest of the problem. So we know the kinetic friction force, and we know the initial speed. See how much we can get done before we even worry about how to solve the thing that they're asking us to solve. So we're just kind of modeling the situation, and then now we know some info, and it's just a game of getting the things in the right places. So we want to know how far it will go, which is this delta x. And we don't have enough kinematic information to get that unless we can find the acceleration, so we want to find an expression for the acceleration first, although we're not plugging in numbers, obviously. So the normal force is equal to mg from the first equation. Substitute that in. And the acceleration is negative mu sub k times g, because these m's will cancel. It's a very interesting result, the fact that the acceleration of the box does not depend on how heavy it is. Little box, heavy box, as long as the whatever the floor is, right? That's what the acceleration will be. It only depends on g and the surface. So the two surfaces for the kinetic friction coefficient. All right, now that I have this, I can go back and look at my kinematics. I know vi, I know vf, I know a now is negative mu sub kg, and I need to find delta x, so I'm going to use this model. Vf is 0. And the acceleration is negative mu sub kg, so I'm going to substitute that in. So move this over to the other side. And divide by everything but delta x, because I want to know how far it'll slide. So vi squared over 2 mu sub k g. And we have 4 meters per second squared over 2 times 0.2 for the friction coefficient, which has no units, times 10, and I'm going to use meters per second squared units here because it'll help me cancel more easily. So in the top I have meters squared per second squared. In the bottom I have meters per second squared. So the second squareds cancel, one of the meters. And so the units on my answer are meters, which is good because that's what I expected them to be. And what we get out of that whole rigmarole is 4 meters is how far the box slides.